China's self-healing concrete breakthrough is shaking the entire construction industry, and the numbers explain exactly why. In lab and field trials, this concrete has closed cracks up to 0.8 millimeters wide on its own. No injection, no patch, no worker touching the surface. You heard that right. A wall healing itself while you sleep. That is roughly a credit card's thickness sealing shut without a single tool. And the crack sealing is not even the headline. Here is the part that blows people's minds. This process can extend a structure's usable life by decades, changing how often we tear buildings down. Click like and subscribe so you don't miss the next one. By the end of this video, you will understand exactly how concrete learned to heal itself. Every poured foundation carries a hidden clock ticking inside it, and engineers finally found a way to slow it down. Ordinary concrete became the backbone of modern civilization for reasons that had nothing to do with luck. It is cheap, it is strong under compression, and it can be poured into almost any shape a building or bridge deck demands. Engineers love concrete because it can carry enormous compressive loads for a fraction of the cost of steel. Manufacturers love it because the raw materials, sand, gravel, water, and cement, exist almost everywhere on the planet. Governments love it because a single batching plant can supply an entire city's roads, tunnels, and housing for generations. Governments love it for a fourth reason too. A nation can build with it fast, without depending on imported materials shipped from halfway across the globe. Picture a bag of ordinary flour, mixed with water and left to sit, hardening into something closer to stone. That is essentially what happens inside a concrete mixer, except the chemical reaction, called hydration, locks the material into a shape it will hold for decades. Here is the part that most people never think about. Humanity now pours more concrete every 2 years than it did in the entire first half of the 20th century, an amount roughly equal to covering the state of Texas in a layer 1 inch thick. That is roughly 200 cubic yards of concrete poured somewhere on Earth every single second of every single day. That statistic alone should make you wonder why, with all of modern chemistry available, engineers never found a way to make it heal itself. So why didn't anyone solve this sooner? The honest answer is that concrete's greatest strength, its rigid, unmoving structure, is also the reason repairing it seemed almost impossible. A material built to never move again is not exactly designed to mend a wound. For most of the 20th century, that trade-off felt permanent. The price you paid for a material this useful, this cheap, and this strong. Every dam, overpass, and high-rise foundation on Earth was built on that same unspoken bargain. It worked. It is still working today, all over the world, in structures most of us walk past without a second thought, structures carrying school buses, water mains, and entire subway systems every single morning without complaint. But brilliance built on a hidden trade-off eventually meets its bill. Somewhere inside every one of those structures, a slow, quiet failure was already beginning. That failure would go unnoticed for years, hidden inside walls, buried under highways, sealed behind concrete facings nobody was ever meant to examine closely. But it would not stay hidden forever. The flaw hiding inside every slab of concrete on Earth is not exotic. It is chemical, and it is structural, and it was baked in from the very first pour. Concrete is strong under compression, but it is weak under tension, the stretching and pulling forces that come from traffic, temperature swings, and the earth shifting beneath a foundation. The moment tension exceeds what the material can bear, it cracks, sometimes invisibly, at a scale thinner than a human hair. Every truck that rolls over a bridge deck, every summer heat wave that expands a parking structure, every winter freeze that contracts it again, adds another small stress the material was never designed to absorb gracefully. This is not about a cosmetic blemish on a sidewalk. It is about a structural vulnerability that lets water and oxygen reach the steel reinforcement buried inside almost every modern structure. Once water reaches that steel, it begins to rust, and rusting steel expands, roughly 7 times its original volume, wide enough to split concrete apart from the inside. The same way ice cracks a water pipe in winter once it freezes and expands beyond what the pipe was built to hold. Engineers estimate that repairing corrosion damage costs the global economy more than $200 billion every year, a sum large enough to fund the entire annual budget of a mid-sized country. Here is the part most people never think about. By the time a crack becomes visible to the naked eye, the damage underneath has often been spreading for years. The consequence is not abstract. Bridges get load restrictions. Tunnels get emergency closures. Water infrastructure leaks silently for decades before anyone notices the bill, sometimes losing enough treated water each year to fill thousands of Olympic swimming pools before a single leak is traced back to its source. For a century, the industry's answer was reactive. Patch it, inject it, replace it, and repeat the cycle every few decades at growing cost, sending crews out with epoxy, sealant, and scaffolding to chase damage that had already been spreading for years underground and out of sight. Nobody was asking whether concrete could avoid the wound altogether. They were only asking how fast they could stitch it shut once it appeared. That question sat unanswered for generations, treated by architects, contractors, and city planners alike as an unavoidable cost of building anything meant to last. In 2019, a team of materials scientists in Nanjing began answering that question with data that was harder to dismiss than anything the field had seen before. The team came from Southeast University in Nanjing, working alongside materials engineers from the Harbin Institute of Technology, two of the institutions most trusted in Chinese civil engineering research. The core idea sounds almost too simple once you hear it. Earlier attempts at self-healing concrete, pioneered years earlier by researchers in the Netherlands, tried embedding bacterial spores directly into the concrete mix, spores that would wake up when water reached a crack and produce limestone to fill the gap. It worked in theory, but the bacteria often died during the harsh, high alkaline mixing process itself, long before any crack ever formed. Most of the healing agent was wasted before it ever got the chance to do its job, and the healing that did occur was often shallow, sealing only the outermost surface of a crack while leaving the deeper structure untouched. The Chinese team's breakthrough was almost mechanical in its simplicity. Protect the healing agent the way a blister pack protects a pill from moisture until the moment you actually need it. They encase the bacterial spores and a calcium-based nutrient inside microscopic capsules, tough enough to survive mixing, but fragile enough to rupture the instant a crack physically breaks them open. The same way a blister pack sits harmlessly in your pocket for months until you actually press down on the exact spot that releases the pill inside. Here is the part that puts everything into perspective. The capsule does not activate on a timer or a chemical trigger buried somewhere in a lab formula. It activates only when damage itself creates the exact mechanical stress needed to break it. Water then reaches the exposed bacteria for the first time, and the healing reaction begins within hours, instead of the weeks earlier methods typically required. A difference measured not in convenience, but in how much damage spreads while the material waits to respond. The nutrient reacts with calcium already present in the concrete, producing calcium carbonate, essentially synthetic limestone, that crystallizes directly inside the crack and seals it from within. Earlier approaches failed because they released their healing agent too early, or never released it at all. This approach only spends its resources exactly where and when damage actually occurs. That is the entire mechanical trick, wrapped inside a shell smaller than a grain of sand, distributed by the billions throughout a single truckload of ready-mix concrete before it ever reaches a job site. But knowing a mechanism works cleanly on paper, is very different from knowing how well it actually performs once real cracks, real weather, and real time get involved. Let's start with the one number that keeps this entire breakthrough honest, instead of glossing over it the way so much science coverage tends to do. Self-healing concrete in its current form can only close cracks up to 0.8 millimeters wide, a gap roughly the thickness of a credit card. Anything wider than that, and the microcapsule system alone cannot fully seal the damage, leaving a gap that still needs a traditional injection or sealant crew, the same crew this technology was designed to reduce, not eliminate entirely. But here is what that number actually means in practice. Research on structural concrete shows that the overwhelming majority of cracks that threaten steel reinforcement, the kind that let water and oxygen trigger corrosion, form well under that threshold, often closer to 0.3 millimeters, roughly the width of 3 sheets of paper stacked together. In other words, the limitation sits almost entirely outside the range where the damage actually matters most, which is exactly where you want a limitation to sit if you have to have one at all. Here is the part most engineers did not expect. The same encapsulation process that enables healing also reduces the concrete's overall water permeability by roughly 20%, even in areas where no cracking ever occurs. Picture a raincoat that not only patches its own tears, but also becomes slightly more waterproof everywhere else simply by being made that way. That is an advantage the original bacterial concrete never offered, a passive benefit that requires no crack, no trigger, no healing event at all. One place this is already winning today has nothing to do with roads or towers. Underground metro tunnels and wastewater infrastructure, structures that are almost impossible to inspect or repair once sealed underground, are proving to be the ideal early application, precisely because a crack here is not merely expensive to fix, it can be nearly impossible to reach at all. When repair access is measured in months of tunnel closure rather than hours of scaffolding, a material that fixes itself stops being a convenience and becomes something closer to essential, potentially saving transit authorities millions of dollars in ridership disruption every single time a closure is avoided entirely. The honest limitation still stands. Wide cracks still need traditional repair, and nobody involved in this research is claiming otherwise, however impressive the early results have been. The question was no longer whether self-healing concrete worked in a controlled setting. The question was which structures needed it first and how fast the supply chain could scale to meet real-world demand. In 2023, engineers with the Nanjing Metro Group applied self-healing concrete to tunnel segments along a newly built underground line, the first large-scale deployment of the material outside a controlled laboratory anywhere in the country. The tunnel ran beneath a section of the city, carrying tens of thousands of daily commuters, exactly the kind of high-stakes, hard-to-access structure this material was built for. Field monitoring recorded crack closure rates within the target range predicted by the original lab studies, healing more than 90% of hairline cracks within 4 weeks of exposure to groundwater, a timeline roughly 1/3 as long as engineers had originally budgeted for the repair window. The field matched the forecast. That single fact matters more in this industry than almost anything else. Because concrete behaves differently under real humidity, real vibration, and real temperature swings than it ever does inside a curing chamber. A material that performs perfectly in a controlled lab and fails once it meets real soil pressure and real groundwater chemistry is worthless to an engineer signing off on a bridge or a tunnel. This one did not fail, and the gap between predicted and observed performance stayed within a few percentage points across every monitored segment. Just as important as the healing itself was how little the construction process needed to change to use it. The microcapsules mixed directly into standard ready-mix batching equipment, already sitting in concrete plants across the country, requiring no specialized machinery, no new training program, and no meaningful change to pour schedules. That compatibility, more than the chemistry itself, is what lowers the barrier between an interesting lab result and a technology contractors will actually choose, because it means adopting it costs a construction firm almost nothing beyond the price of the material itself. Field performance data from the project has since been made publicly available through China's National Infrastructure Monitoring Database, allowing independent researchers, journalists, and even competing engineering firms to verify the results themselves, rather than relying on manufacturer claims or press releases alone. This is not a laboratory curiosity anymore, a senior materials engineer involved in the tunnel project told reporters. If this surprised you, the next part is going to be even harder to believe. Hit subscribe so you're there when we cover it. It started with one narrow application, tunnels, where inspection cost and repair access mattered so much more than the crack width limitation ever could. Then it spread outward from there, into wastewater treatment plants, coastal seawalls facing constant saltwater erosion, and eventually highway overpasses across 3 separate provinces within just 2 years. The claim now had receipts. More than 140 international patent families now cite self-healing concrete technologies developed in China, filed across markets as varied as the United States, Germany, and South Korea, a filing volume roughly triple what the same research field produced just 5 years earlier. These are not academic citations, filed and forgotten in obscure journals. These are legal and financial commitments, the kind companies only make when they expect a technology to matter commercially within the next several years. China's State Construction Engineering Corporation, the largest construction company on Earth by revenue, began piloting the material across 4 provincial infrastructure projects in 2024, with a stated internal target of expanding to 20 additional sites by the end of 2026. Sika, the Swiss building materials giant, announced a research partnership exploring encapsulation techniques for its own product line the same year, backing the effort with an initial research budget reported at $12 million. CRRC, China's state rail manufacturer, began testing the concrete in precast components for high-speed rail platforms, aiming to cut platform maintenance downtime by roughly 1/3 within 5 years. Meanwhile, the European Union's revised construction products regulation now pushes member states toward materials with longer verified service lives, a policy shift that rewards exactly the kind of durability self-healing concrete delivers, and one that construction firms across the continent are already citing in early procurement planning documents. In any market where regulation rewards a 50% reduction in lifecycle repair costs, a 20% price premium on the front end is not a trend. It is a competitive pressure no serious company can afford to ignore for long, especially once a single competitor starts winning public infrastructure contracts specifically because their material outlasts everyone else's by decades. Here is the part that puts the whole race into perspective. The companies moving fastest are not doing so out of environmental goodwill, however good that might look in a shareholder report. They are doing it because the math around lifetime cost, not upfront price, increasingly favors materials that fix themselves before a repair crew ever needs to be dispatched. All of the underlying patent filings referenced here are publicly searchable through the World Intellectual Property Organization's open database, available to anyone willing to look rather than take a press release at its word alone. The corporate scramble was no longer quiet. Confined to conference presentations and academic journals, nobody outside the field ever reads. It was becoming the new baseline every competitor now had to measure themselves against, whether they were ready for that shift or not. If self-healing concrete captured even 20% of global infrastructure concrete demand by 2035, it would represent a material shift roughly equivalent in scale to the entire steel reinforcement industry that emerged over the last century, an industry that today employs millions of people and moves billions of dollars every year. Beyond durability, there is a genuine carbon story here too. concrete production currently accounts for roughly 8% of global carbon emissions, larger than the entire aviation industry combined, largely from cement manufacturing. And every structure that lasts 120 years instead of 50 means one fewer full rebuild and one fewer round of emissions from producing brand new material from scratch. Here is the part most coverage of green construction leaves out. Durability itself is one of the most underrated forms of decarbonization available to the entire industry. But turning a promising technology into a global standard is a long road. And it is important to be honest about where that road gets genuinely difficult. The healing agent currently adds between 15 and 25% to the raw material cost of a standard concrete mix, a premium most municipal budgets are not yet structured to easily absorb. The bacterial spore production process has not yet been scaled beyond a handful of specialized facilities, limiting current global output to a small fraction of what mainstream adoption across an entire national construction sector would actually require. Building codes in most countries, including large parts of the United States, have not yet been updated to formally recognize self-healing concrete as a certified structural material, a bureaucratic gap that can add years to any large public project's approval timeline. The healing reaction slows dramatically below roughly 40 degrees Fahrenheit, limiting reliable performance in colder climates for now, a real constraint for a country the size of Canada or the northern United States. Long-term durability data beyond 10 years simply does not exist yet, because the oldest field applications are barely that old, meaning the full 120-year lifespan projection still rests partly on accelerated lab aging rather than decades of real-world evidence. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem, as much as an engineering one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the climate and the construction industry both demand is a different question entirely. The story of self-healing concrete is ultimately the story of what human civilization can build and where it can build it. For most of history, the places that needed durable infrastructure most, flood-prone coastlines, seismically active regions, rapidly growing cities across the developing world, were also the places least able to afford constant repair and rebuilding cycles. A material that maintains itself, rather than demanding a steady stream of skilled labor and imported repair materials, changes that equation directly. Regions across Southeast Asia and parts of sub-Saharan Africa, where infrastructure spending competes directly against healthcare and education budgets, stand to benefit the most from a technology that lowers lifetime maintenance costs rather than simply lowering the upfront price of a single pour. The access gap remains real today. This technology currently costs more upfront, and the nations that need it most are often the ones least able to pay that premium first, a familiar and uncomfortable pattern in how new technology tends to reach the world. What is genuinely new here, not incrementally better, but categorically different, is a building material that responds to its own damage without waiting for a human being to notice, diagnose, and authorize the fix. That is not a minor improvement. It is a different category of solution entirely. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed infrastructure decay demands is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. Concrete is the single most consumed material on Earth after water, which means even a modest improvement in how long it lasts compounds across millions of structures, decades of use, and trillions of dollars of infrastructure spending worldwide. If self-healing concrete raises a question about what other materials China is quietly re-engineering from the inside out, that story is worth understanding too. And it is the subject of our next video, China's insane breakthrough that just replaced aluminum, the Xiaomi chassis story out of 2026. The link is in the description. If this changed how you think about the materials holding up the world around you, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every 2 weeks. Now, I want to hear from you in the comments. Would you trust a self-healing bridge over one, inspected by a human engineer every single year? Or does self-repair only earn your trust once it has decades of real-world proof behind it?